morning. My name is Arturo Intelisano. I am a physicist, and even if I have studied quantum mechanics and the structure of the matter, I am been working in the field of space in the company Thales Alenia Space Italia since 15 years. My lesson concerns a strange matter, which is information management in space. Is a powerful tool at systemic level to think about the link I said before among segments, among units, and even among concepts in the sense of Bayesian modeling, which is surprisingly easy on the basis of what I have said. Is what we do exactly. We have our opinion, we see how the history works, then we change eventually our opinion in a new branch, and again we reset if some evidence occurs that what we have estimated in a prioristic way is not correct. But again, as I said to you, there have been 300 of discussion, and the discussion is still in intercourse, because behind we are trying to put a sort of border between inductivism and deductivism, and we are trying to define a metric between these words. Why could be so important to use this tool in the space world? Let's see, for example, the small satellite paradigm that it is coming to be used in this period. New consolidated paradigm. With the small satellite you can perform formation. You can think of distributed payload instead of a single payload put in a single big asset. We can use a small launcher. We can use multiple launcher, that is in a single launch vehicle we can insert more small satellites. They can give open design towards modularity, flexibility, because we can design easily and change them according to the function of the moment. They can enhance, being a lot, coverage and revisit time. They can be used for tactical use, that is, you put a specific constellation of class or cluster or small satellite in a specific area because you need that in that time frame. Big assets are a prioristically defined to see some areas, and probably with the time passing you need instead another perspective. They can be extremely useful for operational responsive system. I'm thinking, for example, about military systems. They are capable to be used for reduced lifetime missions, in which, as I said before, the reliability is more on the satellites itself than on the single elements that constitute it. They can be used for commercial off-the-shelf, like many universities have done with the CubeSat, for example. In the plot you see in the bottom part of the satellites, you see how the number of satellites increases the possibility of covering some areas, just because you can put many of them on a single orbit, or modifying their right anomaly, you can perform formation which are particularly able for wide baseline to enhance the on-ground resolution, for example, for radar system, but also for optical system. Now, in this new scenario, cluster of small satellites, we have to think about, in a broader sense, to the probability of success of the entire missions. That is, the capability to provide the required service for a given amount of time. In this new delocalized perspective, delocalized means on more small satellites, we have two basic assumptions. The service capability, that is the availability of the signal due to the physical and geometrical configuration we have of this small constellation, but also the classical reliability and availability concept that apply to the single spacecraft, but which, as I stated before, can be applied, can cause the failure of one or more satellite subsystem, but which can be replaced at satellite level. How the Bayesian approach can be useful in this new perspective? I have made a study in the past to understand how at system level a microsatellite system, where microsatellite I mean many microsatellites, can be studied not only at space segment level and reliability, but considering also the depots that you have on ground, or the system of depots that you have on ground, with many different parts, many different subsystems, that you have to put in place to maintain efficient the entire subsystem. So you have a system base, which is the microsat constellation itself. You have a certain number of ground bases, which are the depots on which you maintain the chain logistic for the replacement of the parts of the single microsatellites. But you have also a conceptual depots, which can be, for example, a certain number of spare satellites that you put in orbit, dormant satellites, which can be eventually activated when you need. So there is a redundancy at two levels. Ground system levels, redundancy means you have a certain number of depots ready to integrate in a short time these microsatellites and to launch them in short time. Must be efficient because must cope with the service availability requirements. From the other side, you can have also a certain number of dormant satellites already on flight but dormant, which can be activated when there is the need. Obviously, being not active, their lifetime is more longer, and so we have to cope with these two worlds and to study with a certain metric how can be managed in a cost also effective way a system like that. In that study, I used the logistic technique approach. Logistic means exactly the same logistic that, for example, IKEA can use when put together and decide how many elements parts have to stock in a single depot at a single time in function of how many persons buy some elements, some products or not. But also, for example, the big car providers, which have the problems to maintain and stock a certain number of the replacement elements in order to be efficient not only for the system of the repairing system, but also eventually for the production system of the car themselves. The logic is basically the same. So you have some statistic on the efficiency of the system, which is the statistic on the failure rate of the single parts, a statistic on the failure rate of the transport system among the single parts, the failure rate about the stocking of the single parts because they have also their single lifetime, the single rate of failure of the elements when active, and so on. Is a dynamic flux, again, of probabilities, which drives the logic and at the end must be summed up and summarized in a single figure which gives you an estimation of how many parts to be stocked, how many costs to be assessed before in order to be efficient in case of troubleshooting, which is risk management. How many number of already available microsatellites to be maintained in order to replace them in due time, and so on. It's not simple. And in fact, this metric approach have many models that traditionally are managed in a frequentist way. That is, history frequentism has said to us that the failure rate has a specific distribution, for example, a typical weighable distribution with a certain lambda, with a certain rate. It's the history which has driven these figures, and knowing that, we built a sort of deterministic approach that must be used and stimulated. Typically, a Monte Carlo approach is used in this case because having a predefined statistic, you have to pick up in a random way all the possibility with the maximum sigma statistic you can have in order to make this distribution to communicate inside the famous logistic scenario I have said before. I have not entered in the detail of the metric, this is the name scenario that is used, there are many, but what is important to me is that you understand the logic behind. And with this random lottery, you try to estimate the mean time between critical failures, which represents the ratio between the time the system is fully operative and the number of critical failures, which prevent the full functionality, and also the availability, that in this case is the ratio between the operative time and the total time. The reliability figure has a particular definition in this context because it is defined as the ratio between the number of missions completed without a system failure and the number of missions attended. But again, I am trying to assess this parameter through a lottery. This Monte Carlo approach has some advantages and some drawbacks. For sure, the advantage is that we can operate on the history of this kind of failures. The problem is that this history can be limited. We have no performed this history on all the mission, and sometimes the availability of this failure rate are also maintained, let me say, not disclosable. Because they are also properties of some company. So it is difficult to infer in a deterministic way a statistic which is limited intrinsically by its logic. Anyway, the logistic approach based on a greedy or metric algorithm are very good to at least understand the complexity of the ground system activities together with the space system where the model finds its resolution. In these cases, it is possible that demand or repair rates not stay constant, or cases in which variances exceed the means. A quite technical expression to say that in most cases we have a not constant variance to mean ratio, and I am introducing a bias. This is the problem with these approaches. But in any case, they can be used when heuristic probability density functions are available in literature, not so spreaded, with fixed means and variances that can be combined among the echelons, which are the various levels. Echelons in the metric system are the various elements in which we model our system, so the various scales. This technique is particularly useful to model dynamics which are more item dependent, which is not always the case. If we introduce the same approach, so the logistic approach, with a Bayesian logic behind, the system can be much more robust to the lack of information we have. Because again, the game between a priori maximum likelihood estimation and a posteriori can be put together in a Bayesian network and estimated and reinforced to the evidences, giving a much more robust and reliable confidence figures on the availability and reliabilities. And according to my opinion, this is the future for this complex system in which we do no more speak only of the single satellite anomaly, the ground system anomaly, the element which must be replaced, but we put in all its complexity the launcher system, the repairing on-ground system, the stocking problem, the depot problem, and so on, with an information which can also be partially dependent on the history. So we don't need not to have all the information, but we manage the information we have in the most efficient way than a frequentist Monte Carlo approach. Why I'm saying this? Imagine what is happening just in this year. OneWeb mission is an example. A great big number of small satellites, for example 700 low Earth orbit small satellites in a sun-synchronous shape, trying to cover in the broadband internet the entire planet. Try to manage 700 microsatellites, their possible troubleshooting. We cannot perform this exercise in the traditional manner, having the housekeeping telemetries from a single satellite, trying to analyze them and then understand what is the problem, and it is not efficient at all. And eventually it must be very cost effective, so eventually they are more risky because they use, for example, commercial off the shelf, I don't know, but simplify the redundancy, not double stream but single stream. So imagine this complexity. Is there a metric or a methodology to assess clearly this in a more robust way? Yes, Bayesian network. To now, I mean up to the present state of knowledge, this is an effective way to manage this big constellation of microsatellites. So, managing anomalies and FDIR, failure detection, isolation and recovery. Yes, we can afford on design complexities with the automatic FDIR and redundancy strategy at a single satellite level. Good, but it means cost. It means complexities at algorithm level and so software and so FPGA and ASICs and so on. Or we can think at a more simple single stream satellites, but with a logic of replacement at a microsat level. Okay, simplified the design, simplified the redundancy logic, but we have to put in mind context awareness, Bayesian approach to be really helpful to manage in an efficient manner troubleshooting before they happens, and to design it before thanks to a Bayesian approach which can say to us which subsystem is better to make more complex, more redundant or not. And in any case, we cannot think at a system which is completely free of ground intervention, because in a sense we have no complete information at all. This is the sense of this lesson, and the rule of the expert is in a sense always behind the wall. As I stated in this slide, in any case the ground station intervention for monitoring and recovery action is difficult to be completely removed, but when the number of small satellites is high, it is necessary to put in place an efficient strategy to support the system efficiency. Also eventually in an automated way on ground. The troubleshooting flux must be optimized. A single ground station cannot manage so many mini satellites in parallel, because there is a limitation bandwidth, because there is a limitation in the post-processing of these telemetries in a fast time, because in any case we could have the need of engineering support of an operational team, if not also of the engineering design team. So the information flux has to be long time processed among all these entities. It cannot work when we have big numbers. So again, efficient manner means prevention, means inference before of the troubleshooting in a most possible automated manner. Okay, I have taken from the internet this amusing history of life when we start from a Homus a priorius. Homus a priorius, we cannot even make inference, just use the things as they are, like a monkey. A Homus pragmaticus, who starts to change the nature in the very simplistic way. An Homus frequentistus, and it lasted for centuries, which start to make models thinking that the model is the basis of his reasoning on nature. Homo sapiens, which is in the middle, that it is starting to understand how much is inductive and how much is deductive. In the modern age, I hope, so far so good, the Homus bayesianis, which tries again to see how much he is able to model reasonably with what he really has in his hands, and not in an absolute prioristic way. We are for centuries, especially from the Illuminist age, postulating a lot. Now we must be more pragmatic, especially when the complexity of the system imposes this kind of rules. It is not so easy to rule out models, to define which model is better than the other, to define which parameter is better than the other. And also in the data regression and model formalization techniques, there is a work to be discovered. Usually what we do, we collect the data, we process the data, we correlate the data, and then we infer information. Seems simple, but this means that we have to understand which are the key parameter definition and model updating in order to be efficient in anomalies forecasting. There are very recent, very powerful ways to infer this. Imagine that you have some data, you have your opinion on which is the best model for this data. I have my opinion on which best model is my data. We have to find the balance between this, knowing some data on the experience of that specific physical process. From Shannon, we have learned a powerful parameter, which is the entropy of a random variable. So we can infer how much information we can gather from a process, knowing is a probability, and this is purely Shannon. It is important because I have now to map this k parameter, the entropy of information, with my model. And as I said before, we can have many models. Which is the best model? And how much complexity can we manage to have a reasonable managing of the information behind this model? There is, for example, a test from a Japanese mathematician called Akaike, which, for example, give us a parameter that can discriminate from one model to another, not in an absolute sense, but in a relative sense, saying to us, the lower is the parameter, the better is, if the ratio between the number of parameter k in this formula that we use and the maximum value of the estimated likelihood, we can infer between some models and some parameters, mediated by some parameters, which is the most efficient in terms of information. Or we have a standard ANOVA tests, which means based on variance test, which again in regression techniques give us a feeling, a sense on how performant is our model. Sometimes standard parameters that we have learned at school, like the mean or the standard deviation, for example, are not so efficient parameters in the frame of a specific distribution. So these techniques are extremely helpful, even if still not so largely used in engineering discipline. They are more largely used in economics, because economics is strongly devoted to management of probabilistic distribution, but instead they are extremely powerful in managing as I said before, Bayesian network approach. In the new small satellite vision, in which a space system can be composed of a large number of these small satellites, we have a sort of clouded information paradigm, where clouded information can have different meanings. For example, the payload can be spread on more satellites, or you can have the same payload on the same satellites, but you have to collect together the information from the single satellite, because at system level you use the batch collected information to obtain the final mission topic. For example, in the radar system you use baselined information in order to reconstruct stereo images, and you can put more satellites in order to improve the on-ground accuracy. But in any case, to collect data from different platforms can be also useful for what I said before, having a batch network Bayesian system which is able to fill in advance a possible troubleshooting that can happen in the future. So this clouded information, this mixed information, must be centralized for processing, for data collection and for analysis, to create embedded statistics and parameters and model definition in a more efficient way. A fundamental concept is that, in any case, Bayesian modeling is not an automatic model procedures, is not what the Greeks said a panacea. The role of the expert is fundamental in defining the K parameters and information fluxes, as well as a priori estimation and topology of these networks. So, in conclusion, from this lesson, I have tried to give just some topics in a very wide, large, general perspective, in order to stimulate some advancing in the engineering of space discipline, especially for what concern in general the data management and how it influences the design and the cost of a space system. The modern data processing techniques are profoundly changing the way in which information is analyzed and managed. Technology of a space system based on small satellite is introducing these new paradigms, especially for what concerns information flux. Bayesian statistical techniques are particularly suited to analyze design reliability as well as to identify strategy and the metrics in terms of FDIR and troubleshooting management. Design simplification and use of commercial off-the-shelf components for cost reduction impose this metric to assess reliability not only at the unit or at the subsystem levels, but also considering the overall system. Logistic approach analyzed through Bayesian network give the possibility to assess the entire project in an end-to-end way. Data mining, which is how to gather information from the data, and machine learning techniques can be adopted to monitor and to define optimal troubleshooting in case of big constellations. And in any case, is key that the role of system expert is fundamental in defining influence models and key parameters to be assessed and monitored. Thank you.